Yeah.
Yes, okay, so the next speaker is Prasanna Venkatesh from India, and he's going to talk about readout of quasi-periodic systems using qubits. So could you go ahead?
Yes. Hi. Good morning, good afternoon, good evening, wherever you are. Thanks a lot to Manas and Bhabani for organizing such a nice meeting. And giving me an opportunity to talk about our work, our recent work. And it's really wonderful to be able to sort of meet people, at least online in these sort of gloomy times, and keep the discussions going. My talk today will be about the following sort of cartoon version of what I'm going to talk about is presented as a cartoon picture here. We are basically going to consider an one-dimensional quasi-periodic chain, and we will couple qubits to either one qubit to a single site or couple of qubits to two sites, and use the qubits to read out the properties of the chain. We will read out both the way single particle eigenstates of this chain look, as well as also directly read out how transport in such a system should look. This is the point of my talk, and to sort of situate this within the different topics that are going on in the conference, I would say that I am more on the open quantum system side, though you will not see a master equation or a non-Hermitian Hamiltonian. And still, it's okay, because my training in some sense is in quantum optics, and I've always approached an open quantum system from the point of view of quantum measurements, which is, in a way, as I hope to convince you, a controlled way of opening up a system. And that's the sort of flavor that I take. So I hope my pointer is visible. If not, please let me know. And this is work in collaboration with Madhumita Saha, who's in the audience, who is a postdoc with me, and we work together with Vijay. And Madhumita has just recently moved on to IISER Pune to do a postdoc there. And she also has a poster on this up. And you can also address questions after the talk. You can write to her, and yeah, you can ask her about this. Okay, and this is published here. This is the paper that I'm going to talk about. Okay, so this is the brief outline of the talk. I'll first try and motivate the problem that we studied. Why is it interesting to us? And following that, I'll describe the exact setup and also convince you that this can be a problem that can be solved. In fact, exactly. And following that, and tell you about how this readout that we are planning is going to be implemented, and finally finish with some results from the calculations that we have done. Okay, so moving on to the first section. As Vijay nicely emphasized, in these last 2 decades, there's been a great explosion of quantum technologies, right? And there have been many interesting engineered quantum systems, and studying these systems, we have been able to answer some basic questions as well as create interesting application. One important idea within this sort of this revolution of quantum technologies is this idea of quantum simulation, where what you do is you basically take a hard to control very complicated system, and in order to study it, you make an analogous system using very well controllable systems. Okay, so you basically simulate in an analog manner a very complicated system, and using this idea of quantum simulation, we've been able to do a lot of very interesting physics over the years, and some examples that we now can actually engineer very interesting, strongly correlated Hamiltonians and study their phase transitions and whatnot. But as we see this quantum simulation, in order to be able to get here, one thing that we had to learn to do very well was control individual quantum systems in an excellent manner. Okay, so the quantum simulation story, in some sense, has been a story of better and better quantum control as well, which meant that something interesting is added on top when you sort of try to simulate interesting quantum systems in this analog manner. Not only do you create interesting Hamiltonians, study their phase transition properties, But you also, because of the availability of this extremely interesting quantum control, you find newer and newer ways to probe and measure the system. Okay, and there are multiple sort of interesting ways to measure a quantum system. In this talk, I'm interested in a particular class of such probes, which I'm going to broadly call as in situ quantum measurement. What is the idea here? This is especially suited to studying quantum dynamics. The idea there is basically you have your system of interest, you do not directly measure it, you always have some other ancillary system that's coupled and you measure the ancillary system. There are many advantages to doing such a way of measuring things. One advantage is that you can essentially continuously measure your quantum system. That is one advantage. The second advantage is you're getting the readout could help you in sensing. You can sense things because you get collecting more data in a much more advantageous fashion. And finally, from the point of view of just quantum measurements, you can also ask interesting questions because measurement and dynamics are going on at the same time. You can ask like, what is happening to the system in terms of measurement back action? So these sort of questions can be asked, and hence this idea of in situ quantum measurement is quite interesting. And this has been implemented in a variety of systems. I'm just giving a couple of examples in cavity QED or in circuit QED as, for example, in the last talk, which I was basically talking about. So in such systems, you have your system of interest coupled to a cavity or a resonator, and you read out the resonator and learn about the system. In this line, I want to basically talk a little bit more in detail about one particular kind of in situ measurement that has been implemented in ultra-cold atomic systems. And this is what I'm picturing here. So this picture shows a very neat experiment from the group of Arthur Videra in Mainz, where what they've done is they've taken an rubidium atomic cloud and they have trapped it in a so-called optical lattice, so which is basically a light-induced periodic potential. And this is standard. This is the sort of standard tool of quantum simulation, and you can do interesting physics with it. But what they actually do in this is they then take individual cesium atoms and they can move this cesium atom in a controlled manner into this rubidium cloud. So it's basically in a very controlled manner with position resolution, they can actually implant an impurity into this rubidium cloud, which means you can do very interesting measurements of local measurements of this atomic cloud using this cesium because you have independent control of this impurity and the gas. One of the recent things they have done is they have implemented a very beautiful single atom thermometer where the temperature, the motional temperature of this rubidium atom is encoded into the spin degree of freedom of this cesium, pseudo spin degree of freedom of the cesium, because they can have collisions that are spin exchanging. So it's one of the smallest thermometers that you can think of, and it's very important. It's not just cute. It is important because this rubidium is in very low nanokelvin temperatures, and it is generally hard to get a very accurate measurement of temperature at such low values. So this is one example, and this will hopefully be a sort of motivation for the sort of readout scheme I'm going to propose.
Okay. Sorry, Prasanna, sorry. I have one naive question. What is the coupling between the cesium and the rubidium here? What is the kind of coupling term?
So it is just collisions, but it is spin exchange collision. So when the collision happens, there is also some angular momentum exchange. So not just S-wave collision, let's say. So you can actually exchange angular momentum. So what happens is basically the cesium's level separation is 1/2 the rubidium's level separation. So if you want to excite the cesium, you have to absorb a phonon from the rubidium. So, or something like this. So as a result, what happens is you can actually read out the motional temperature of the rubidium. The collision is just spin exchange collision, standard collisional interaction. There is nothing fancy.
Okay, thanks.
Yeah. Okay, so and hopefully all of this sort of long introduction is to convince you regarding the first part of what we are doing, which is we are going to propose a kind of in situ quantum measurement, and this is very interesting, or in sort of this ways in particular systems point of view, but also in a general way. As I said, this is a controlled manner of opening up a system, and it's also an interesting approach to open quantum systems. So that's one motivation. So the second part of our motivation is what is the sort of system we would like to probe. As I said in the title, we are interested in the so-called quasi-periodic systems. So in order to sort of introduce the quasi-periodic systems, I want to start with the more well-known cousin of this, which is basically a system that is a tight binding lattice. Consider a quantum particle that hops on a lattice, and the on-site, and it has two parts to this dynamics, right? So it can tunnel between different sites, and it can actually also feel some on-site potential. Now, if this on-site potential is a random number with uncorrelated random number, something interesting happens. This is what happens is this phenomenon of Anderson localization. What happens is, as you change the strength of this disorder, how big this disorder potential is, after a sort of a threshold strength, all the single particle eigenstates of your system can get localized. Otherwise, it's an extended block wave, but then it becomes localized if the disorder is very large. And in fact, this statement I made, I have to qualify it a bit. It depends a little bit on the dimension. So for example, in 1 and 2D, basically it is, if you increase the threshold beyond a certain point, you'll always get localization. All the single particle eigenstates get localized. And on the other hand, in 3D, you get a so-called mobility edge, which means that in your spectrum of single particle energies, states above a certain energy will be localized, but states below that energy will be delocalized. So you have both localized and delocalized phenomena, localized and delocalized single particle eigenstates. So this is the famous Anderson localization picture, which has been continuously studied since the 50s when it was proposed by Anderson. A related kind of system is called a quasi-periodic system. In a sense, this is neither a completely periodic setup nor a completely disordered system. So one sort of paradigmatic system in this quasi-periodic landscape is this so-called Aubrey-Andre-Harper. I'm going to call this AAH just because it's a little bit easier, lattice, which is basically, and generalizations of this AAH, which is basically, we can forget about dimension. Let's just focus on one dimension. It is, you can think of it as being the tight binding version of taking two periodic potentials that are incommensurate, meaning their wavelengths are basically irrational multiples of each other, and taking a tight binding limit. So this would typically give you this AAH kind of potential. And the interesting thing about this quasi-periodic systems, because of this, you can easily implement them experimentally, as I will mention in a moment, but also they have very interesting properties. What do they show? In this generalized AAH, for example, you can actually have a mobility edge even in one dimension, unlike this Anderson localization where you need 3D. So, and that is very interesting. And with the regular AAH, you have very similar physics to Anderson localization in the sense that you can, once the potential, this quasi-periodic potential strength becomes above a threshold, you will get localized states. Okay, so ever since sort of this quasi-periodic and Anderson localization, they've been sort of studied for a while, and they've been actively studied continuously in this transport community for a long time. And what I would like to emphasize is that even sort of people outside that community, like me, for example, have now been attracted to this in the recent times. And there are some reasons that I can think of for this resurgence in the study of quasi-periodic system. The chief reason I would say is basically there are multiple experimental realizations available now. The most obvious one is from 2008 up to now in 2018, where you can actually implement quasi-periodic lattices for ultra-cold atoms, right? So that is one very well-known implementation, and which is very nicely studied. A second, more recent development, which is I'm going to emphasize by looking at this very recent, beautiful experiment from the groups of Alberto Amo and Bloch, who will give a talk later, Jacqueline Bloch, is basically you can implement this with photonic lattices as well, polaritonic devices as well. And in fact, you can even do, which is very beautiful to see, that the degree of control now with these polaritonic devices, where you can actually make what's called an AAH lattice, but also make a discrete quasi-periodic lattice, and you can tune between them in a very beautiful manner. And this is just beautiful. The degree of control now with this systems is rivaling ultra-cold atoms more or less. And so there are multiple experimental realizations available, and this is giving more attention to this field. Secondly, this question, even from the time of Anderson, there's been this question, like what I told you about localization was with single particle states. Then what happens if I add more particles and particles can mutually interact between them. So then there is this interesting physics that can happen, that even in a many body system, you can actually get localization. And this is now receiving great attention. So because you can actually predict localization and measure it with such nice systems, even with many body systems. And this connects nicely to whether many body system thermalizes or not, because you would generically expect that localized systems may not thermalize. Okay, and finally, a nice final connection, which is making this study of quasi-periodic systems very popular, is you can now consider open versions of these quasi-periodic systems. For example, within this sort of lattice systems, you can consider open systems due to losses from each site. Atoms just leave the site. That is one way of losses. But you can also consider theoretical schemes where, like Abhishek and Achak and Manas have considered, where you can attach paths to the edges of this AAH and study transport in the sort of standard mesoscopic way of studying transport. So there are multiple interesting things you can do with quasi-periodic systems. And I hope that I've convinced you that this quasi-periodic systems and in situ readout are both worthy pursuits. And my talk is going to be, just to having convinced you, this is the talk. So I'm going to talk about this AAH chain, couple qubits to them, and try to read out the nature of the single particle eigenstate, and also directly read out transport properties in the sense that how does an initially localized wave packet spread, the rate of spreading of initial localized width of an initially localized quantum wave packet. That is the sense in which I mean transport. And I will show that we can do all of that by coupling qubits. Okay. And I just want to emphasize that qubits as quantum probes is not something that we came up with. We are the first people to come up with. There are multiple people who've been, ever since the dawn of sort of qubit age, people have been trying to couple qubits to systems and study them. So it's a fairly developed field. There are many big players in it, and you can see all the references here. Okay. So now I can move on and talk about my exact system and talk about the dynamics. So the system has two parts to it, the qubits and the AAH chain. Let me begin first by describing the properties of this generalized AAH chain. So the Hamiltonian is, as I said, a tight binding Hamiltonian, and there is this term which is the on-site potential. It has a constant part, which I'll come to in the end. This is some constant chemical potential offset, and this is the part that is called the generalized AAH, where B here is an irrational number, and there are two parameters, lambda and alpha. Lambda is the strength of the quasi-periodic potential. And in addition, there is this hopping term, and the hopping strength, I am going to typically set it to 1 most of the time, but I will still keep this J around when comparing and sort of talking about regimes of transport, because it will just make more sense, just in case you don't remember J is 1. But all calculations are at J equal to 1. Then you can just, this is simply a quadratic model, so you can really easily diagonalize this and calculate the eigenstates, which are what I'm going to be calling as SPEs, or single particle eigenstates. So now, this is the generalized AAH model. When you take this alpha parameter to 0, you get the AAH model, and the physics of this AAH model is simple. So when your lambda, this strength is very small compared to J, lambda is less than J, all of the single particle eigenstates, which I'm plotting here, so lambda 0.1 and 0.5, these are extended over the lattice. When lambda is equal to J, they are what are called critical. I'll in a moment qualify what one means by critical. But when lambda is greater than J, you basically get localized single particle eigenstates. So this is the property of an AAH model. One can actually sort of quantify this by using something called this inverse participation ratio, which is basically this quantity where you take an eigenstate and calculate its amplitude at a given site and sum over all possible eigenstates. Okay, and then when you look at the behavior of this inverse participation ratio as a function of the number of sites of the lattice, when everything is extended, you basically have no scaling with n, but when everything is localized, the scaling is n to the -1, and in between, when they are critical, it is n to the -b, with some positive number b between 0 and 1. Okay, so this is one way of quantifying what I just said using some perfect measure, using a measure. Okay, so now let me look at the generalized AAH model and tell you the properties of that. Again, the single particle eigenstates can be solved for, and now alpha is non-zero, and I'm going to be in this regime where alpha, lambda are both greater than 0. Then once your energy, this energy scale, mu plus 2j minus lambda over alpha, falls within your spectrum. What happens is all states, eigenstates with energy less than this mobility edge are extended and greater than E are localized. So for example, as I increase lambda, you will see that initially everything is extended, and as lambda becomes larger, a mobility edge will enter and you will localize some part of your spectrum, and then you will localize more and more states, and at very large lambda, at a given alpha, you will get all states localized. So this is the idea with this generalized AAH model. But the interesting thing is you can have coexistence of extended and localized states. Okay, so that's the general summary of the properties of this AAH and GAH, generalized AAH. And now I'd like to go on and talk about the single qubit scheme, coupling scheme that we propose. So this is, okay, is there a question?
Can I ask a question? So could you go back to the previous slide? So in this case, you only have a single mobility edge, right?
Correct. Yeah.
Is there any possibility that you have multiple of mobility edges?
Within this GAH, no, but sorry, is there someone?
Sorry?
I can hear someone else. Okay, I think there is some crosstalk, but
okay, yeah.
So what I'm saying is that with the generalized AAH, this model alone, no, but I think I'm not sure, because there is a zoo of quasi-periodic potentials you can think of.
Right.
Whether one can do it with other models, I'm not aware of. Maybe at the end of the talk, you can come back to it, and there are other people here who might know this better. Yeah.
Yeah. Thank you.
Maybe I had a comment.
Yes, Manas.
So indeed, there are various variations of this model which have two mobility edges and so on and so forth. There are various generalizations, not of there is not of this type, but some other variations where you can definitely have more structure. Yeah.
I see.
Okay,
thank you.
That's what I would anticipate. Okay, good. So then let me go on to the qubit coupling scheme. So basically the idea is I have this AAH, generalized AAH chain, and at one side of the generalized AAH sign, we basically couple a single qubit, and this qubit coupling is of this form: sigma Zi Ci plus Ci dagger. Ci is the on-site operator. Okay. And of course, once you diagonalize this AAH chain, you can rewrite this Ci in terms of the eigenstates of your chain, single particle eigenstate operators of your chain, and you get this coupling coefficient that tells you how much the qubit couples to each eigenstate k. Okay. When you write it in this form, it becomes immediately obvious that this coupling is nothing but the simple spin-boson type coupling. Moreover, it's the dephasing spin-boson coupling, because this interaction couples with the Hamiltonian of the spin. You can exactly solve for the dynamics of the spin. Okay, and our idea is that we want to read out the properties of the chain from the dynamics of the spin. That is the basic idea. So which means I want to convince you that just a slide to convince you that I can do this. I'm just going to present the result. The idea is that if you start with some initial state with the spin in some state rho s and the chain in a thermal state e to the minus beta h over z beta, what I can do is I can write down the exact solution for the Heisenberg operator of the Heisenberg operator of the spin. Of course, sigma z of the spin does not evolve, but the sigma plus and minus evolve. And what I can do is then basically write this operator in terms of both in terms of the initial Heisenberg spin operator sigma minus, and in terms of an displacement operator of the chain. Okay, so but more important than this is the dynamics itself, which means I'm interested more in the expectation value of this coherence of the qubit, and one sees that the qubit's coherence is damped, right? So this is basically what one means when he says that this is a dephasing path. So if you start with some initial coherence in your qubit, as a function of time due to the coupling with the chain, you get damping. So this damping rate is precisely given by this expression. Okay, and one thing that we do is we choose here. I can make a comment on the chemical potential, on-site chemical potential. We choose it such that this spectrum is positive, so that we can define this thermal factor cot h without any issues. Okay, so that's the solution for a single qubit. Now, and then of course, just as a small thing, you can separate out this dephasing into two parts. One part that occurs when there is no temperature. So if beta is zero temperature dephasing, and then there is some part that purely comes from having temperature non-zero in the chain. Okay, so we look at both, and qualitatively temperature doesn't play a very important role in this in the sort of physics that I'm going to talk about. Okay, so then the next thing I want to motivate is why do you want to do 2 qubits? So what we will show is that the single qubit dephasing rate already encodes the nature of the single particle eigenstates, but we want to do a little bit better, and the motivation is as follows. So a standard way to sort of parameterize this transport properties of such AAH type models is to look at the width of a initially localized wave packet as a function of time t. So the width evolves, and this width evolves as some power law t to the eta, and when eta is 1, when you have extended eigenstates, single particle eigenstates, and then this transport is called ballistic, and this eta is 0.5, this is diffusive, and this happens when you are at this critical point of this AH when lambda equal to j, and eta is 0 when you have localized. Okay, so this way of characterizing, this is basically an implication of the single particle eigenstates for the transport, right? So we want to be able to also see if we can directly measure this exponents eta from our readout. Okay, that's what we want to do. And what we are going to do in order to get there is we would want to couple 2 qubits at sites I and j. So the difference in the sites I minus j will play the role of the width of the wave packet. And we will see that the because of them coupling to this AH chain, they will get correlated, and the time scale on which they get correlated will play the role of this t here. And from just looking at the correlation dynamics of these 2 qubits, we can actually read out this eta. So that's the second scheme we want to try. And it's essentially a very simple extension of the first scheme. So now I have 2 qubits at 2 sites, and each of them is coupled via the same sigma z coupling. And there is the AAH chains Hamiltonian here. And again, because of this nature of this sigma z coupling, one can exactly solve for this covariance of these two operators. We have chosen this sigma minus sigma plus, but this you can choose any sort of spin operators and you can get the signature. This covariance is just sigma minus sigma plus at time, sigma minus sigma plus average minus sigma plus average product, right? So this covariance actually you can see if I start with initially uncorrelated qubits where this average is equal to the product. So it's mean field. If I start with such an initial covariance 0, due to the coupling with the qubits, due to the coupling with the chain, you essentially develop correlations. And there are two factors that lead to correlations. This is this generalized lamp shift parameter, and there is this correlated dephasing parameter. These are individual dephasing that I already wrote down. This is the correlated dephasing. All of this you can really exactly write down. Nothing hard to do about this. Okay. So that's the setup, that's the dynamics. Now we are at a good point to go on to the results, right? Okay. So let me begin. Let's first consider this single qubit. In the first part of the results, I'm just going to focus on the simple AAH chain, and then I'll come to this generalized AAH model because the AAH chain has, it's somewhat simpler to explain. Okay, so here is basically a plot of this dephasing rate as a function of time, okay, for a AAH model with some 610 sites, doesn't matter. But what I would like to point out is basically as we go from lambda, so here j is 1, as we go from lambda less than j to lambda greater than j, we see the following behavior for the dephasing rate. So for lambda less than j, the dephasing rate is in blue. I'm sorry, it's not super clear. The dephasing rate basically oscillates very little and quickly settles down to an average value about which it oscillates very little. Okay, but once you're in this localized regime, lambda greater than j, you see that the oscillations are very pronounced and the damping rate does not settle to some average value. Okay, so let's understand why this is happening. So if you look at the expression for the dephasing rate, you see that it is a sum over an oscillating term with the oscillation rates given by the single particle eigen frequencies, single particle eigenstates energies, right? So now when you have extended states, what happens is basically the coupling, the qubit couples to multiple eigenmodes. Okay, so there will be many frequencies that contribute to this sum, and that's what leads to this damping. On the other hand, when you have in the localized phase, there is only one or very few eigenstates that couple to the single site, namely the eigenfunctions that are localized at that site, right? So those are the only eigenstates that couple, and as a result, you would get a much more oscillatory term here. In order to confirm this intuition, we can just plot, inspired by this sort of participation ratio, you can just plot a measure of how many eigenstates couple, and one can see that when you are in the localized phase, basically this object does not scale with n, but in the delocalized phase or extended phase, this participation ratio that we are defining actually scales down with n, saying that there are multiple states that are coupling to your qubit. Okay.
Sorry,
Manas. Yeah.
I have one question. So in this expression for gamma I, so at this stage you evaluate the sum numerically, right?
Correct.
So
always numerically. The reason is, if it is basically a usual periodic tight binding lattice, then you can actually convert this sum to an integral and get some analytical expression for the sum. But in the AAH, the spectrum, I don't have a closed form, so I am not able to do the sum analytically, but one can easily evaluate this for extremely large n. Yeah.
Right. But for the localized regime, presumably there should be some way to simplify this, right?
Yeah, I mean, for the localized regime, the basic simplification is I would just write it as 1 minus cos omega k0t over omega.
Right.
Basically, that's why you see those oscillations. Yeah.
Right. Because here, otherwise, to convert it to summation, we don't know really how to think of the density of states also, right? So there is that's also complicated here.
That is complicated, and I just heard from Juzar yesterday that there are some papers where you can even think of writing some version of a density of states for this discrete paths. I have to maybe we'll come back to this in the end, because Juzar commented that one has to also look at that carefully, because there is some subtlety regarding revival times, for which this density of states might be important. That's my understanding, but I understand that it is a discrete thing, so I don't know how to really think of this density of states in a very, in a rigorous manner here. You're right.
Okay, thanks.
Okay, so that's the physics of this single qubit dephasing. But now what we have seen is that qualitatively there is this oscillations when you have localized, and there is the damping out of the dephasing rate in the extended phase. But we can sort of put all of this information into a single parameter. The idea is that you can look at this so-called information backflow, where you look at the time derivative of the dephasing rate and look when does it become negative. When it becomes negative, the idea is that there is basically backflow of information from the path to the qubit. Okay, and this is an indicator of this non-Markovianity, and you can very simply calculate this indicator by summing over all intervals where you have this gamma, this time derivative negative. And very nicely, when you look at this non-Markovianity measure as a function of the AAH parameter lambda, you see very clearly that the non-Markovianity, the magnitude of non-Markovianity, just to be completely clear, I'm not saying that everything is Markovian here. What I'm saying is that the non-Markovianity's extent and the size of it very clearly increases at the localization transition. So by just measuring this non-Markovianity parameter, you can actually get a readout of which phase you are in very nicely. So that's the first sort of readout that we are proposing. Okay. So then the second mechanism that I talked about is this transport readout, and let us actually look at what happens there. So there I can actually present the results directly. So what am I plotting here? So basically this is the, let's look at the first plot here. I'm plotting basically this covariance measure between the two qubits coupled at sites I and j, and I'm plotting the covariance measure as a function of time. So now I am in the regime where lambda is less than j. So I'm in the extended regime. And what we see is that there is some threshold time t star after which the qubits get correlated. Initially, they are uncorrelated, and t star is the time it takes for the correlations to develop. And here we have plotted this t star with t over I minus j, and we have evaluated this for different sites I and j. And we can actually plot this threshold time of correlation as a function of I minus j, and we see that t star is proportional to I minus j. What is this? If you think of this I minus j as basically the width and t star as the time, this linear relation basically tells you that this eta parameter that tells you how width scales with t to the eta is 1 here. So this can give a direct readout of this eta. So that's the first thing we can see. Then the second thing I'm plotting here is at lambda equal to j. So this is the critical regime. And very nicely in this critical regime, again, there is some threshold time after which there are correlations independent of how far away you are. And very nicely, this threshold time scales as I minus j squared. So this width is t star to the half, and this eta is half, indicating this diffusive regime, and this is the ballistic regime. Okay, so from these two qubit correlations, we can very neatly read out the kind of transport you have in the system. Okay, so that's the second thing. And then the final thing I want to say is, how does the two qubit correlations look in the localized regime? So that is very nice. What we can do is we can wait for the extremely long times. Basically, in principle, in a perfect sort of situation, I should never get correlations in the localized regime. But what you can do is you can measure the correlations at essentially extremely long times as a function of separation. And it is predicted that this should fall off as an exponential, and the factor in the exponential is basically the localization length is 1 over log lambda, and we see that scaling very nicely. So we can, in some sense, in the localized regime, we can read out the value of lambda from looking at the qubit covariance at long times. Okay, so this is yet another very nice way to read out the system. Okay, so that's the sort of the gist of the main results. Now I want to, and this was all for the AAH model. I just want, in the last one, I have a couple of minutes.
Yes, you have 4 minutes.
Okay, so in the last couple of minutes, I just want to show the results for the generalized AAH model. There are some subtleties, but it is more or less straightforward to extend. So let's first look at this non-Markovianity measure. So what happens in the generalized AAH model? This is this alpha lambda plane. What I'm plotting here is the fraction of localized states. So in this regime, there is no mobility edge, and all states are delocalized. So to the left of this line, and to the right of this black line, all states are localized. In between is where there is a mobility edge. So the first thing we find is when everything is localized and everything is delocalized, in that regime, the non-Markovianity measure, independent of which site I couple to, is a fairly decent representation of the fraction of localized states. But when I'm actually in this regime where I have a mobility edge, what happens is that the extent of non-Markovianity strongly depends on which site I couple to. Presumably, this is not crazy, because at the end of the day, it depends on whether in your spectrum there is a state localized at that particular site that can decide the extent of non-Markovianity. So this site dependence is somewhat expected. So now for the transport, we can again do long time correlations. And what I'm plotting here is long time correlations in different regimes. Again, there is a site dependence, but the important thing here is that you can still have, when you are in completely localized or completely delocalized, this long time covariance is a very good measure of your system, right? So you get long time correlations if you have enough delocalized states, and you do not get long time correlations if you have only localized states in your spectrum. In between, there is a subtlety. So what is the subtlety? The idea is that whenever I have a mixture of localized and delocalized states, the nature of the delocalized states is what is going to determine what sort of transport property I get. So for example, here I'm looking at 3 different values of lambda and alpha, where you see linear scaling because there are localized and delocalized states. But as you go from basically red to green, as you go from green to red, your fraction of localized states is increasing, and the slope of T star versus I minus j increases, which tells you that the number of localized states increases, and hence it is taking longer for the two qubits to get correlated. So that's one thing we can find. On the other hand, if I sit on this critical line where there is basically a mixture of localized states and critical states, there is no completely delocalized states, then of course the scaling is dominated by the critical scale, which goes as I minus j whole squared. And in both cases, you can use again this property to find out what sort of states are actually causing the spreading of correlations. Okay, so that's the result for the generalized AAH model. And now this brings me to the summary and conclusion of my talk. So what we have shown is that we can actually couple to a JAH chain either with single or double qubits and read them out. With single qubit, you can use Non-Markovianity and read about, find out the single particle eigenstates nature, localized, delocalized. 2 qubits, I can get correlations. And finally, with the experimental implementation, we have taught preliminary things about it. One thing is that the single qubit, the best prospect is basically the first experiment I showed you where I can implant ultra-cold impurities. With multiple qubits, it's a little bit more subtle. One has to probably look at solid state implementations because you have to also implement 2 qubit gates to read out these correlations. So outlook, so we could think of extending this to situations with non-dephasing coupling, where we can actually study two things. One is, could you directly get signatures of transport? Like, can you measure current? That is one very nice thing if one could do. Secondly, this will also mean that the back action of the qubit on the chain can become very interesting in this regime. And those are some of the questions that one could look at. That's it. Thank you. And also please talk to Madhumita. She did all of the calculations, and it would be great. Yeah.
Okay, thank you very much, Prasanna, for the beautiful talk. And now it's time for questions and comments. So are there any questions?
Yeah, hi. Are there any cases like where all the states are like power law localized, and what would be the phenomenology of this dephasing in those contexts?
So, I mean, I am thinking that the critical phase is like that, right? So I have to understand what you mean by power law localized. So because lambda equal to j, I would think that these are all power law localized in some sense, but I might be misspeaking the terminology that you have in mind. So you do see this I minus j diffusive transport there, but if you mean something else, one has to think. So that we have already covered in the model. So basically that is what I think, yeah.
So in lambda is equals to j, are all the states localized in generalized AAH model?
No. In the AAH model with lambda equal to j, they are not localized, but I think they have this. So if you let's just go back to pictures instead of words. So let me just go straight to the first slide where I had these wave functions plotted. Right. I hope I had a lambda equal to j. So let's see. Yeah. Sorry. Here, so this blue line, right? Well, it's not yet localized. So this is, so lambda equal to j is not localized. So it is what I would call critical, but I don't know what, I don't know if this is the same as algebraic localization. Lambda greater than j, I understand very well. There is this exponential localization. But from this plot, I cannot say, maybe there is a more expert in this system that can answer. Like, I don't know, Manas, is this what you call as algebraic localized? I don't know.
I mean, yeah, it's basically neither localized nor delocalized.
Right, right. So it is not, I don't think it's algebraic localized. Then.
I mean, if you measure something like, if you calculate something like IPR scaling with system size, and you get some fractional powers.
Correct. So if,
right. I say enriched minus b.
Yeah. So then one can say that, yeah, so in this sense, it is some kind of algebraic correlation or whatever you want to call it. But I don't know. Yeah. This is part of the study. This sort of systems we can read out here. Yeah.
Okay. No, in the long time limit, typically, like for the extended case, one would expect this dephasing function to scale linearly with the time. I wanted to know if you have this critical localization of these states where you have IPR going like power law. So what happens to the long time limit of the dephasing function? Does it scale linearly with time?
So the thing that I am trying to show here is that when you are in the long time limit and you have localized states, the dephasing function doesn't settle down at all. So it is oscillatory. So I mean, there is a mean of it that stays constant somewhat, but it is oscillating, right? So if I have localized phase, but in the sort of delocalized phase, it actually settles down to some value, right?
Okay. Thank you.
That is what is happening.
Okay, thank you. Maybe these oscillations in the delocalized phase, are they finite size effects?
So I don't think any of the things that I'm showing here are finite size effects in a sense. But if, for example, one finite size effect that I can think of is if I wait for extremely long times for any finite n, I'll get some revivals after this blue. That is there, but I am cutting off in some sense here where there is no revival yet. And the idea is that this represents in some sense an approximation to the reality with n infinite that I am cutting off before revivals. That's the.
So what does this period of these oscillations correspond to
So in the
delocalized case?
In the delocalized case, it doesn't correspond to any one frequency, right? So it is basically it is this sum. So it has a sum over many frequencies. Okay. So it is some fairly complicated sum over different oscillating terms. But in the localized case, it is precisely that eigenstate that is localized at your qubit couplet site. That frequency omega, that is what is oscillating.
Yeah. Thank you.
Yeah.
Okay, so we are behind the schedule, but is there any short question?
Can I ask one? Okay.
Yeah.
Yes.
Prasanna, so this, I mean, you're trying to probe this system with this qubit.
Right.
So one question is like, it wasn't clear to me. I mean, are you also now making measurements on the qubit, and how does, I mean, because that's finally you don't need to make measurements, and that will affect the dynamics.
So right now, this is very, very sort of, let's say, proof of principle. And I completely think that is the outlook, that now if you measure the qubit and then does it affect the localization property, that is the back action. That I have not at all studied. We have not at all studied, and that would be an interesting direction to go. Now the question is the dephasing coupling the best scenario to study it, because there cannot be exchange of energy in some sense, and so I am not sure with the dephasing coupling how far what interesting results you may get by back action, but definitely if I have like a proper energy exchange coupling, this would become very cool to study, and that's something that is interesting.
Okay, thanks.
Okay, thank you, Prasanna. So now